I think we can start now. Hello everyone, thanks for coming. It's my pleasure to introduce Anahita, our speaker today. She completed her PhD here in UCR, and she was actually Brian's first graduate student. And now years have passed, and she is a staff scientist at IPAC Caltech. And recently, she has been a deputy task lead for NASA Science Center at IPAC. And so without further ado, please welcome Anahita Alavi.
Thank you, Nilufer. Thank you for the introduction. And it's the NASA Science Center for Euclid only, just to make it quite. But it's a great pleasure to be here talking to you, even though remotely. I wish I could be there in person, but life is complicated, so I couldn't. But I'm very happy for this opportunity. So today, I want to talk about some recent work that I have been doing for measuring the dust attenuation in high-redshift, low-mass galaxies, which in this call, I will be calling them dwarf galaxies. But what I basically mean by dwarf galaxies is the star-forming galaxies with the stellar masses below 10 to 9, and also, these galaxies have low metallicities. So whenever you hear dwarf galaxy from me, that's the type of galaxies I'm talking about. And then we want to understand how the dust attenuation is in these galaxies. And that would be the first part of my talk. The second part, which will be a very short part, I will also like to talk about because I realized that this new organization is a student organization. So I thought that might be useful if I talk a little bit about IPAC, what do we do at IPAC, and also different opportunities that exist for either students, graduate students, postdocs, or for more permanent job, if you are interested. So the second part of my talk will be for that, but it will be very short. So here, I would like to start with these images. On the left actually is a video. So it's an combination of some images taken by JWST, near-cam camera, and also MIRI for NGC 346, which is the largest, brightest star-forming region in a Small Magellanic Cloud. You know, a Small Magellanic Cloud is a local dwarf galaxy, basically satellite of Milky Way, and this beautiful image shows, even though it's a dwarf galaxy, but how complicated the dust structure is in this dwarf galaxy. Warm dust emitting as red color we see here, also pH dust. So the goal of this work is to look at dwarf galaxies similar to SMC or LMC, but at higher redshifts. And by high redshift here, I mean basically cosmic noon, between redshift 1 to 3. And on the right side, you can see some of the galaxies that we will be talking today about them. These are basically lensed galaxies, star-forming galaxies, very low mass at redshift 1 to 3. And the goal is to understand if how the dust attenuation is in these galaxies is similar to what we see in SMC or other local dwarf galaxy, or it's different. This is the outline of my talk. First, I will talk about just some basic introduction. Why do we care about dust? And why do we even care about dwarf galaxies and measuring dust for dwarf galaxies? Then I will introduce the sample that we use for this study, 2 different samples. And then I will say, how do we measure dust? And then showing some results. And then a little word about future, very near future with Euclid. And then at the end, again, the second part, which is not science. So first, why does dust attenuation matter? Why do we even care? So dust grains are not just a simple component in galaxies, but actually they are crucial in our understanding of galaxy physical properties, or in general galaxy formation and evolution. Dust grains absorb, as we all know, dust grains absorb the light scatters the light in different wavelengths, including ultraviolet and optical, and then re-emits the light at longer wavelength, for example, infrared. So therefore, just thinking about that, the dust is actually changing the shape of the spectrum of galaxy. This is the spectrum that we use to measure different galaxy properties. So in order to basically measure the intrinsic physical properties of the galaxies, we always need to correct for dust, whether we are measuring the star formation rate from ultraviolet light, or we are measuring the star formation from H-alpha emission line, or we're measuring some sort of physical properties, for example, metallicity or ionization state of ISM, using the line ratios, we always need to correct for dust. So that is why it is important to understand the dust attenuation and correct for that. But then the question is that, okay, then why do we even care about dwarf galaxies? I guess there are many answers that we can give to this question, but maybe the best answer is the simplest answer. And the simple answer is that because dwarf galaxies are the most abundant galaxies in the universe at all times. Here, I'm just showing an example of a study by Boyens et al. 2021 of UV luminosity function, which is basically luminosity function, but just for people who are not familiar with the term, it's just the number density of galaxies at given, of course, a volume and then wavelength. Here we're looking at UV luminosity function. And then in the plot, you can see how the UV luminosity function is changing from redshift 2 to very high redshift 10, as shown with the purple points. And as you can see, a different redshift and going to higher redshift is even more. As we go toward fainter galaxies, which are at the right side of the plot, the luminosity function is much steeper, meaning that the number density of dwarf galaxies is much higher than the more massive, more brighter galaxies. So there are many of them. So it's important to study them. The second reason is that over the past decade or so, there has been many studies suggesting that dwarf galaxies might be one of the important contributor during the ionization era. So we know that during the ionization era, the ionizing photons reionize the universe, right? The question is that where do these ionizing photons coming from? And one answer could be dwarf galaxies, that not meaning that they create a lot of ionizing photons, but because there are many of these galaxies, even if they create a little bit, and those photons can escape from the interstellar medium into the intergalactic medium, then at the end we will have a lot of ionizing photons. And here is a study by Finkelstein in 2019, where on the y-axis, they show the cumulative ionizing emissivity, basically the number of ionizing photons at a given volume per time. And then they see how much, what fraction of ionizing emissivity is coming from galaxies at different UV luminosity. Again, going to the right side of the plot is where the fainter galaxies are sitting. And as we see, it seems that more fraction of ionizing radiation is coming from fainter galaxy. And it's not just that they create, they might be dominating the ionizing radiation, they also significantly contribute into the non-ionizing ultraviolet budget at different redshift. This is a plot from work that I did during my PhD that we showed that at cosmic noon, redshift 1 to 3, the dwarf galaxies, basically faint galaxies, they contribute maybe more than 45–50% of non-ionizing ultraviolet budget at those redshifts. And there are many more different reasons that why these galaxies are important, which there's no time to talk about that. But I wish I could convince you that why it's important to study these galaxies and especially measure dust. So for this talk, we will be using two samples of dwarf galaxy. The first sample, which is listed on the left, I will give more details about these samples, but just briefly introducing each sample. The first sample is a sample of lensed galaxies. These galaxies are located behind three massive foreground galaxy clusters as listed on the left side. So because of the strong gravitational lensing from these massive galaxy clusters, the galaxy located on, behind are magnified, so therefore we are able to see them. The galaxy in this sample have been, the spectra for the galaxy have been obtained with MOSFER and Keck over several years, and so this will be our first sample. The second sample is from JWST, a passage program, which this is a program we had on cycle 1, where it's a pure parallel program, which I will talk more what that means, but it's basically using nearest spectrograph on JWST to use the Grism spectra from nearest in order to basically target the cosmic known galaxies, and that would be our second sample. So starting with the first sample, which basically the data will be, the photometric data will be from HSC and spectroscopic data from MOSFER. So in this sample, we have 33 lens low mass star-forming galaxies between the redshift 1.4 to 2.6. The histogram on the left shows the distribution of the stellar mass for this sample. And as you can see, our galaxies are actually all basically below 10 to 9. That's why we call them dwarf galaxy. And then the median stellar mass is 8.3. On the right side, you see distribution of spectroscopic redshift for this sample and also distribution of UV absolute magnitude. Again, you see that the galaxies are very faint. And these UV magnitudes are corrected for lensing magnification. So this is intrinsic. Just to show just an example of how do this galaxy look like, this is one of the clusters that we have here, in actually my favorite cluster, because that's where I did my first project in PhD. This is ABL 60 and 89, very massive lensing clusters. And just to show one of the galaxies that we have in this sample from these clusters is this beautiful sort of blue dwarf galaxy. And then what you see here is the multiple images of the same source. So because of the strong gravitational lensing, we might give more than one image for a single source. And the spectra of the basically the image in the center is shown on the right. So you see H alpha and you see H beta here from J band spectroscopy with MOSFER. You can also see O3. But of course, not for all the galaxies we have H beta detection. For some, we have non-detection, which we put some sort of limit. Now the question is that how do we measure the dust? Dust can be measured in many different ways, right? Or on different wavelengths. For example, if you want to directly look at the dust, you have to go to like mid-infrared or longer infrared wavelength to directly observe the dust. But here, what we do, we measure dust using two techniques. One is using what we call it UV spectral stop. So this is first time was suggested by Caltech in 1994 in her original famous paper that if we look at the UV spectrum of a galaxy, and by UV basically means between 1200 angstrom to like 2600 angstrom, very blue. The spectrum of the galaxy can be parameterized as a power law. Very simple, lambda to the power of beta. And the power in this equation, what we call it beta, is the UV spectral slope. And the dust, it can be a tracer of dust because depending on how much dust attenuation exists, this slope could be red or blue. So people have been using UV spectral slope as a tracer for dust, especially at high redshift, where direct observation of dust was impossible and now hard. So that's one way, which we call it basically a stellar dust, because this part of the spectrum is mostly coming from the stars. So we are looking at the dust covering the stars, right? That's why we call it a stellar dust. The second way, again, introduced in Caltech in 1994 paper is using what we call it Balmer decrement. It's basically the ratio of H alpha to H beta emission line. And that is also a measure, that is also a way of measuring dust, but it's because the H alpha and H beta emission lines are coming from H2 region, star forming regions. For this technique, we are basically looking at kind of what we call nebular dust, dust in the nebula region. And that's another way. So we use these two ways to measure dust for our sample, both samples, the MOSFET sample and also from JWST. So UV spectroscope is tracing dust, right? So it is not crazy to assume that UV spectroscope should be somehow correlated with what we call it TAUB, the Balmer optical depth or Balmer decrement, because both are somehow tracing some kind of dust in the galaxies. And it has been shown over the past years that yes, these two basically quantity are correlated, but in different ways. For example, back in 1994, again in Caltech paper, a sample of local star-based galaxy, they showed how the UV spectral star on the y-axis is correlated with the Balmer optical depth on the x-axis. And that solar line is basically what you would expect, the kind of slope that you would expect from Caltech attenuation curve. Later in 2015, there are many more papers, which I'm not listing here. I'm just listing maybe the more important ones. But 2015, from MOSFET sample, and probably you guys are all familiar with MOSFET because some of the MOSFET PIs are in UCR. Navin Reddy, 2015, they had a paper where they looked at the normal star-forming galaxies at cosmic noon, redshift 1, 2, 3, and they looked at this sort of correlation between UV spectroscope and Balmer decrement. And what they found is that, shown with blue red lines here, that depending on specific star formation rate of the galaxies, they could be following one of these curves, which basically the attenuation curve that they found is a bit maybe flatter than what the Caltech was. And then later, again in 2020, Shivai et al. Using the same MOSFET sample, but splitting the sample based off the metallicity of the galaxies, they also introduced two dust attenuation curve for lower metallicity and higher metallicity, and saying that the lower metallicity, the attenuation curve for the lower metallicity galaxy is probably steeper than what we see for the metal-rich ones. And then, okay, more recent one by Andrew Battesi, 2022, from WISP sample. WISP was a pure parallel observation with HST using WISP-3 GRISM. They also found a correlation between beta and Balmer decrement. And this is basically the sun line here. So it has been studied, but most of this study are actually basically on for like more massive, above 10 to 9 galaxies, normal star-forming galaxy. Here, we want to do the same thing, but for the dwarf galaxy, for lower mass galaxies. And the orange squares and orange diamonds are basically our stacks, or we did, in addition to the stack, we did another way of measuring the mean. Is what we see for our galaxies. And the green line here, there are many lines here, it might be a bit confusing this plot, but if you just look at the green solid line here is the SMC curve, what we expect from SMC curve. And the galaxies, this UV spectral SO versus the Balmer decrement for the dwarf galaxies in this study is best represented with the SMC curve. And this is basically some kind of it has been suggested before by other studies as well. And the other line here is the cyan line, which is from Shivai et al. 2020 from MOSFET samples for their lower metallicity sample. And as you see, our galaxies also follow that as well. Basically, that dust attenuation is very similar to SMC because SMC is also a low metallicity. So basically, our dwarf galaxy from this study can be represented with SMC, or as well as also with Shivai curve from the low metallicity subsample. For the next, basically, result, we wanted to see how the dust attenuation is correlated with other physical properties of galaxies, and how does it evolve with redshift, even if does it evolve with redshift or not. So it has been shown over many different studies that dust attenuation, the nebular dust attenuation, is actually correlated with a lot of galaxy physical properties like metallicity, H alpha luminosity, even H alpha equivalent width, and stellar mass. And it has been shown that apparently stellar mass is one of the primary correlation that has one of the primary correlation with dust attenuation. So here I'm showing just listing 3 examples of the studies in literature. On the left is a study by Shapley et al. 2022, again from the MOSEF sample, where they show that the nebular dust attenuation on the y-axis, how it is correlated with the stellar mass, and the same sort of analysis, again Shapley et al. 2023, but using JWST series data from redshift 2.7 to 6.5. Again, the relation, how the dust attenuation is related with the stellar mass. And another similar study from this sample, Battisti 2022. In all of these plots, the gray data points that you see are SDSS galaxies, local SDSS galaxy. And then the color data points are whatever from those papers at higher redshift. And the important takeout from all of these studies is that the nebular attenuation versus the stellar mass relation seems to be not evolving with redshift, meaning that at a given stellar mass, the galaxies, this star-forming galaxies in this sample, have the same nebular attenuation at redshift 1, 2, 3 as local SDSS galaxies. And this is interesting, like why this is happening. That's not what we expect, right? But these galaxies, as you can see from the plots, are mostly focusing on the kind of more massive end, like 10 to 9 and above. And here we do the same analysis, but focusing on the lower mass end. Again, the orange stacks here, as you see, kind of extend this relation down to stellar masses, lower stellar masses, down to 10 to 7. And we see the same basically result, that this relation, dust attenuation, nebular dust attenuation versus stellar mass, does not significantly evolve with redshift at these lower masses, and the galaxy seems to be sitting in the same parameter space as the local SDSS galaxies. So don't ask me why, because this is still a lot of debates and people have been trying to explain it, but it's really challenging. And wherever they try to explain it, there is some caveat, and so it's still on debate, but it's very interesting. So the second, I want to move to second sample, which is from JWST. So on cycle 1, JWST dual programs, we were awarded 383 hours of pure parallel observation with a nearest spectrograph on JWST. This means that wherever there is some primary observation going on with JWST, some team are using NearSpec, or some team are using MIRI or whatever. On parallel side, our team will use the nearest spectrograph to obtain grism spectra, to obtain grism spectra from some random field in the sky. Because it's pure parallel, we don't have any basically control on where we are looking at. It will be just from some random field. But so all the observations for this program are taken now, a total of 383 hours over 63 individual fields. And on the right side, you can see the map, how our 63 individual fields are basically spread all over the sky. And so one thing about the pure parallel program is that because these are random fields, for some of the fields, they don't have any ancillary data. So, and basically this is the first time we are using nearest to just look at this random field. But for some of them, we're lucky, and then they might overlap with some of the famous surveys, extragalactic surveys, that there are tons of ancillary data, for example, cosmos, which happened actually here for our fields. So for those fields that have ancillary data are the fields that we have started our science, because for the rest of the fields, we are observing more ground-based data in order to be able to do, like, for example, acidity fitting or measuring galaxy properties. But one other thing about pure power observation, it's great because it's kind of free. But the thing is that the way that the observation will be scheduled is very limited based on whatever the primary observation is doing. So we do not have that much control. So if it was us, we wanted to get as much as filter as possible and as much as orientation for the Grissom spectroscopy. But this all depends on the primary observation. So wherever we can, we go for it, and we get more filters. For some of the fields, we have Grissom spectroscopy up to 3 filters, 115, 150, and 200, and not even multiple filters, but also 2 different orientations, because different orientation Grissom spectroscopy allows us to decontaminate the spectra from each other and have a more clear spectrum. But if the primary observation is not basically changing the wheels, then we have to stick with just one single filter. Anyway, so this is just one example of one of our fields on passage and the dispersed image from Grissom. So it's great, the Grissom observation, because you get a spectra for all the sources in your field. For those fields where we have 3 Grissom wavelength coverage, it allows us to get access to multiple wavelengths, right? Multiple emission lines, H alpha, H beta, OT lines, O2, and some other even fainter lines if we go deep. And then so we can do different science. We can measure star formation, we can do metallicity measurement, we can do dust attenuation, and so on, which a dust attenuation is the one that I will be talking about. So here I am showing the among these 63 fields on passage, 18 of them are located have overlap with the Cosmos field, and this is great, right? Cosmos have a lot of ancillary data from HST, from ground-based, from multiple other observatories. So that gives us a great opportunity that now we can use this ancillary data to do our science. I'm going to show the dust attenuation plot, the same plot that I showed for the lens galaxies, for only one field from passage. We started with this one field, and then of course we are now in the process of adding more fields. And the field that the results are based on is this one field. Field 28 is one of the fields overlap with Cosmos, where we have 3 Grissom coverage, wavelength coverage. And then here is the preliminary result, again, the dust attenuation versus stellar mass plot that we showed before, and now adding the JWST data, the blue symbols, and it's the same basically result that again, this relation seems to be not evolving with redshift, and the galaxies with the same stellar mass, lower stellar masses below 2.9, seems to have similar dust attenuation, which is very low, it's basically 0 as we get to a lower masses as SDSS galaxy. So JWST data is amazing, and we are now in the process of recalibrating our the data for passage with the new calibration files. So hopefully we can add more fields. But in very near future, we have Euclid now, but very near future, the Euclid data will be public soon. And then it provides now a spectra for thousands of galaxies. So as you know, Euclid is a ESA mission. and it's a 1.2 meter telescope, not very big, but very large field of view. And one of the main goal for this mission is to study the dark universe, right? The expansion of universe and dark energy. And it has two instruments, WIS instrument, which is optical, and NISP instrument, which is infrared imaging and spectroscopy. And then it's Grism spectroscopy, very similar, basically Grism spectroscopy as JWST. But the Grism redshifts from Euclid, they provide 30 million galaxies, the redshifts for 30 million galaxies with H alpha line between redshift 0.9 to 1.8 because the field of view is very big. And here I'm just showing the very first Grism dispersed image taken by Euclid back in 2023, where the telescope was launched. It was launched July 1st, 2023. And then this is a ESA mission, but NASA is partnering with that. And NASA has a science center, as we call it inside at IPAC at Caltech, where there our team, we are involved in the data calibration and then data archive. And then, but the good news is that the first public release of the Euclid data, we call it Q1, is March 2025, and it's actually March 19, 2025. So if you're interested to use this data, stay tuned for March 19, and then the data are amazing because in the Q1 data, there will be data on, so you might know that Euclid has two surveys, wide survey, which will be basically observing an area of 15,000 square degree on the sky and providing Grism spectra for that. But of course, not very deep. But then there is also Euclid deep field, which is 53 square degree of the sky of these 5 fields listed here, but much deeper than the wide survey. And then Euclid deep field will be really amazing for these kind of studies that we want to go to like lower masses or for measuring, for example, dust attenuation. Yeah, so this is basically, I guess, very interesting for the scientific community or whoever wants to look at high redshift emission lines. So this is, I want to just leave this is the summary for the science part of my talk. And basically what we learned here is that we looked at low mass star forming galaxies, as we call them, dwarf galaxy at cosmic noon, using two sample of lens galaxies and also a sample of low mass galaxies from nearest spectrum on JWST. And what we found is that first, when we looked at the nebula dust versus the stellar dust for this dwarf galaxy, they seem to follow the same attenuation curve as SMC and local universe, or the attenuation curve for the low metallicity galaxies at similar redshift cosmic noon as probed by the MOSTEF sample, Shiva 2020. Also, one other thing that we learned is that when we look at the nebular attenuation versus the stellar mass for these dwarf galaxies, it seems to be not significant evolution with redshift with respect to what we see for local galaxies like SDSS galaxies. This has been seen before for more massive galaxy, but here we show that lower mass galaxy also follow the same trend. There will be what we learned from passage says the same thing, but this is just one of the field on the passage. We are now in the process of adding more data, more fields to the passage, so we can basically the plot that I'm showing here, we can have many more galaxies with better data reduction, better line measurement. For the second part of my talk, as I said, I just wanted to give a very short introduction about IPAC, because one thing is that I guess it's important, especially for the graduate students and the postdocs, looking into like future, like the kind of jobs and positions that they're looking for. It would be good to look at other places than the universities, because all the positions in the universities, you're kind of familiar with it, right? This is where you study. But like positions at like places like IPAC might be uh, um, a little bit less clear for you. So I just thought that it might be useful for you, to give you an idea, because it's also very close. You can just drive 40 minutes and just come here and just visit. So IPAC, just starting from history, back in 1985, IPAC was established on the campus of Caltech as the Infrared Processing and Analysis Center for the data, as the science center for the data taken from the infrared astronomical satellite IRAS. So that's how it started. But over the past 40 years or so, IPAC has been growing a lot beyond the name that it was given. So today we simply call it IPAC. It's not Infrared Processing and Analysis Center anymore. It's IPAC. And the reason is that now it covers and it supports a lot of missions, different wavelengths. It's not just infrared. So it partners with NASA, JPL, NSF, and also ESA to support the worldwide research community through different categories: science operation, data archive, and community support. And then the science that people at IPAC do covers basically whatever science you can think of in astronomy, from exoplanets, solar system, to asteroids, and then to like very high redshift universe, early type galaxies, and cosmology. IPAC provides a range of support for many missions. Now currently 20 missions and projects, either in the space or on the ground. Here I'm just listing some of the missions that either in the past IPAC has been supporting, currently, or in the future. So in the past, you probably know that Spitzer, one of the basically very well-known missions that IPAC has been supporting, and it was a science center for a Spitzer mission, but also the same for Herschel mission. Currently, it is supporting many missions. I'm just listing some of them here. For example, Euclid, which we just talked about it, or New Wise mission, which is ZTF and an XI. And then in the future, it will be a science center for many more missions coming. Roman, you probably know about Roman telescope. The idea is very similar to Euclid. It's a 2.4-meter telescope, larger than Euclid. And again, it will be study the dark universe. But Roman and Euclid kind of complement each other. Euclid will be looking at a very large area, 50,000 square degree, but shallower. Roman will be looking at 2,000 square degree, but much deeper. But the idea will be the same, basically, Grism spectroscopy. And then, but more missions like LTB, you might know about that, lunar trailblazer, which will be studying the water on the moon, or Spherics, or UVIX, which is one of the new, basically, ultraviolet mission from NASA, that the launch time is expected to be at the end of 2030. The reason that I'm listing these missions here is that each mission means a lot of opportunity for students, postdocs, and also permanent jobs as a staff scientist. And so IPAC is just it's a group of 160 people working at IPAC, which most of them are staff scientists, 40%, but we have technical staff or developer, 30%, and the rest of admins. Regarding the opportunities for student, postdoc, and staff opportunities, for postdocs, at most times we have at least 10 postdocs or more. So there are a lot of opportunities. If you are interested, I have the the QR code here, you can just scan it and then see list of all the positions available, including the postdoc positions, because again, of all those missions, there is always some postdoc position available. Then there are a very good opportunity for the graduate students. We have an IPAC visiting graduate fellowship. It's a 6 months fellowship for graduate students who are interested in doing some research at IPAC. Usually it happens between February to August, but it can the timeline can change as well depending on the project, and then the next application opens in summer. So for the graduate students, I strongly recommend this because there is tons of projects that you can look at the list of all the projects available. And then if you're interested in any of them, you can just apply for that, and the application is very easy. And not many people know about that. So that's why if you are interested and you apply for that, it's very likely that you might get it. There is lots of opportunity, of course, for undergrad and high school, which I don't go through it. But then also for the people who are now in the position of like thinking about more permanent positions as a staff scientist, I also strongly recommend it because this is here, I'm showing the distribution of current staff experiences at IPAC regarding of the years that people have been here. About 40% of our current staff scientists are the people that have joined IPAC since just last 5 years. This means that there has been a lot of positions available, right? So people could apply and get the job. And and there are a lot of positions available now and in the future, again, because of all the missions. One other thing from this plot is that 30% of the people have been here for more than 20 years. So it's not only a good place because of the multiple, a lot of positions available, but it's a good place. People stay here when they come. So it's just to give some like more data to students and postdocs who might not be aware of this kind of jobs that exist. And if you have any more question about like what exactly a staff scientist does at IPAC, I'll be very happy to answer. So here, I'm not sure how much time I have left, but I guess we have good time left for questions. I leave my summary here, and thank you for this opportunity.
Thank you. Time for a question. So for Anahita. Should come forward.
So, thank you for your presentation. And sorry, it might be a naive question, but on one of your slides, you mentioned that logarithmic ratio of H alpha to.
Sorry, can you come closer because it's like there's some kind of echo which I cannot hear well.
My question was about one of your slides that you mentioned that logarithmic ratio of H alpha to H beta is an indication of dust, or is a good way to measure dust. Could you please explain why?
It's here. You want to know why this is a tracer of dust?
Yes.
Okay. So I'm not sure if I don't think I have the equations here, but basically, let me just go to the paper. Maybe I have it somewhere here. Maybe just looking at the paper, I guess, will help you to see why it is connected to dust. But basically, the H alpha and H beta have two different wavelengths, right? And then H beta is lower wavelength, H alpha is higher wavelength. And then the ratio dust is like H beta will be more absorbed by dust less than H alpha. And then that's how just you can think of why this is a tracer of dust. But just to give an example, just to give from the equations. So just as a definition for like the the dust attenuation, we know that if the intrinsic if the light basically is let's say the H alpha light is intrinsically from galaxy, in order to calculate the observed H alpha, we can use the equation like this, right? For the considering the dust attenuation, the amount of dust attenuated for the H alpha light, that's the observed H alpha flux. The same thing we can do for H beta. And then when we look at the when we just take the ratio and assume some intrinsic ratio for, like, let's say if there is no dust, let's assume 2.86. This is from some physics, that if there is no dust in some like case-free recombination condition in ISM, then the ratio of the H alpha photons created in the star forming region to the H beta ratio, just from physics, will be 286 in some conditions, some assumption about the temperature or the electron density of your ISM. You get that 2.86. So then whatever deviates from this ratio of H alpha to H beta, your observed one, whatever is deviates is based because of dust. And then this is how basically it is related to the reddening. You assume some dust attenuation curve, and then you basically you connect that Balmer decrement ratio to the reddening. I'm not sure if I explained it well. Okay, sure. Let me just go back to the plot. Okay.
Hi, Nadia. This is Archana. Great talk.
Good to see you.
You too. I had a quick question on your NIRIS sample. So how do you estimate the stellar masses and metallicities from, I guess, the NIRIS data?
That is a very good question. So our stellar mass measurement is not from NIRIS data. So in our GRISM observation, when we do the GRISM observation, for each GRISM observation, we also do a direct imaging. For example, when we get the GRISM in 115 filter, we also do the direct imaging. So if we are lucky, we have 3 direct imaging, 115, 150, and 200, where we can do some sort of a CD fitting, but it's just 3 filters. For the plots that I showed, our mass is from Cosmos catalogs, because the field that I showed is in the Cosmos field. So of course, Cosmos has a very extensive, like rich catalogs from HSC, from ground-based, so a lot of different multi-wavelength data available. We just SCD fitting, we just get the stellar mass. But for those fields that are not in Cosmos and just random fields in the skies that never have been observed before, we have some we have a HSC program for some of the fields to observe with both WIFC3 and ACS. Now it's WIFC3, getting some optical images. So then combining those optical images with the direct images that we have from nearest, we can have some filters and then do a CD fitting. For some of them, that's for, I guess, 7 fields. Another program that we have is field ground-based observation, again, to get some imaging in optical mainly, to be able to measure the mass for the galaxies. But that's why we started to do the analysis with the fields in the Cosmos field, because there is where we have the ancillary data, so then we can measure the mass or other significant parameters.
Okay, so the metallicity also comes from the Cosmos data for now.
No, the metallicity, actually, there's another group in our team. They are measuring the metallicity using the O3, using the O3-O2 line ratios.
Okay,
O3 to H beta. And then they are doing the metallicity. So the metallicity is also coming from the spectra. Yeah.
Okay, thank you very much.
Anahita, this is Faiza. Thank you for a great talk.
I have a question. So you said that between stellar metallicity, between stellar mass and metallicity, and in metallicity we are talking about oxygen abundance. It doesn't evolve with redshift.
With dust. What I said is dust, not metallicity.
Sorry.
Yeah, dust.
Okay, dust. Okay, so now it does make sense for me.
Yeah.
Okay. Another question. So you said that you are using Cosmos data to get a stellar mass, and it means that you are using photometric data.
Yeah.
So my question is that how reliable are those stellar masses that we are getting here?
That's a good question. Well, that question always exists, right? Because it depends to like the SED fitting code that you use, like how many bands you have. Well, at least for Cosmos, with all the photometric bands available, not just from ground, but from HSD. I think, and for the mass ranges that, and also it depends to which mass ranges I'm talking about. Am I talking about like 10 to 6 stellar masses galaxy? No, I don't believe those stellar masses. But if I'm talking about like 10 to 8, 10 to 9 from Cosmos 2020 catalog, considering all the available data from Cosmos, I guess we can trust us. But that's a good question, because even with the Cosmos data, even with the Cosmos catalogs, with all those rich, that's one of the richest extragalactic fields that we have, right? Like people have been observing Cosmos fields for forever using HSD, ground-based, whatever. Even when you look at the stellar mass estimate from Cosmos, depending on how you do your photometry, how you do your SED, still there are, especially as you go to a lower masses, there is like big error bars or like a scatter for the stellar mass measurement. But I guess that's best we have now.
Thank you. Thank
Yeah,
you.
sure. And then one other thing about, especially not just stellar mass, but in general the SED fitting, is that some of these fields are also in the Cosmos web, which means there are JWST near-cam data available for this. We are also working with the Cosmos Web team, so then we can add those near-cam imaging also to our photometric catalog. So then, of course, for the SED fitting, our SED fitting parameters will be even more trusted as we add the JWST near-cam data.
No more questions. Thank you, Anahita. Thanks for the talk.
Thank you, everyone. And I really hope to see some of you here at IPAC for our graduate student visiting fellowship, or just if you are interested to come and give a talk or anything, yeah, just shoot me an email. And I hope sometime I finally will get to come and visit UCR in person. Hi, Brian. Good to see you.
Okay, thank you.
Sure. Thank you, Nilüfer. Have a
Bye.
good day.
Bye.